In the previous video, we had talked about Chassis equation. Today, we are going to talk about what is perhaps the most important resistance law in open channel flows, namely the Manning's equation. So we have noted Chassis equation as V equal to C times square root of the product of hydraulic radius and the slope of the channel for uniform flow. So this is Chassis equation for uniform flows. So what Robert Manning did was combined a set of empirical equations and came up with his own version of the expression for the velocity, which got later modified in this form, where the velocity is given by 1 upon n, where n is called Manning's roughness coefficient, Manning's n, and it is related to the hydraulic radius raised to the power of 2/3 and the bed slope raised to the power of half. So this is the very famous Manning's equation. And if there is one single concept that I want you to retain in this course, if you can afford to forget about the other topics that we talk about, although you really should not. But if there is at all, if I have to pick one idea from this course which you cannot afford to forget for the rest of your careers as civil engineers, it would be Manning's equation. It's one of the most simple as well as effective formula which works even to this day, where you can see that the Chassis coefficient, Chassis roughness C, is relatable to Manning's N, and they are related by this equation. C is hydraulic radius raised to the power 1 by 6 divided by the Manning's coefficient. Now let us talk a little bit about Robert Manning, who was an Irish engineer, popularly known as Bob Manning among his friends. So Robert Manning was born in Normandy in France, which is famous for other reasons. Operation Overlord. So Normandy in France is famous for Operation Overlord, which happened, of course, much later than Robert Manning's works on hydraulics. So because Manning was born in France, he had a lot of respect for the French engineers and hydraulicians. I don't know if that's a word, but he had a lot of respect for the works of the French people related to hydraulics, and he studied their works. Manning never really had a formal education on his own, none in engineering, and he has therefore the tendency to derive equations which would be simple and effective. So what he did was combine a set of several, in fact 7 of them. So Manning combined 7 then existing empirical equations relating the velocity to the hydraulic radius. And he took about 170 observations with varying hydraulic radius, ranging from 0.25 meters to as high as 30 meters. And using those observations, he proposed a formula for the average velocity that he obtained from these 7 existing empirical relations, and came up with the formula for the velocity relating to the hydraulic radius raised to the power of 2/3 and the slope raised to the power half. And here he had used another constant. It was later that it was related to the reciprocal of this roughness coefficient n, and that's how the form of Manning's equation, which is popular today, came into being. Now, so this equation is used by hydraulics engineers as well as structural engineers. anywhere, if you have a uniform flow and you need to get an estimate of the velocity, this formula will be used. And what are some of the ranges of these n values? So n is 0.015 for well-laid brickwork and concrete, whereas it is roughly about 0.022 for uniform earth channels. So this was, now remember, Manning's work came about 100 years after Chessie's work. In fact, more than that. So this is 19th century, whereas Chessie's work was in the late 18th century. So about 100 years or so from Chessie's work did the Manning's formula came into existence. And like I was mentioning in the previous video, the equation for Chessie's roughness estimation, so that could eventually be related to modern fluid mechanics. Similarly, for Manning's equation also, links were established between this empirical relationship. So this is also another empirical relationship. This is empirical. This could also be related to modern fluid mechanics and concepts from boundary layer theory. In fact, experiments with real life data and also from Nikuradse's, this is also from Nikuradse's experiments. It was found that the friction factor is inversely proportional to the hydraulic radius raised to the power of 1/3, and we know from our earlier discussion the relationship between friction factor and Chessie's coefficient C. If we use that, then we can write that G by C square is inversely proportional to the hydraulic radius raised to the power of 1/3, and this eventually gives us the relationship between C and R. And therefore, this also confirms this relationship, confirms Manning's equation. This is because if we use this relationship onto Chessie's, essentially what we get is Manning's. So eventually truth was established via experimental observations also, and these experimental observations also show that Manning's n is roughly proportional to the roughness. So if you remember from the previous video, Ks is the roughness height. So Manning's n is proportional to roughness height raised to the power of 1/6. Manning's equation is also known in the Europe particularly as Strickler's equation. Let me use some other color. Strickler equation. So what Strickler did was he did a lot of experimental observations on real life channels and canals, and he related the roughness coefficient n to the D50, which is the median size of the bed material. So the bed, if it's earthen, it would consist of coarse grains, and those grains would have a distribution of their sizes, and the median size of those grains is represented by D50. This is in feet. And when we use D50 in meters, in SI units, then this relationship is a little modified. And when you have a mixture of bed materials, as what happens in reality, this empirical relationship takes this form. Now remember here that Manning's equation, this constant 1 is for SI units. It would be 1.49 if you are using the FPS system, which is popular in the US and so on. So in the next class, we are going to discuss a little more about this Manning's roughness factor N. See you.